Today we're going to talk about a project that I recently completed, which is a battery-operated candy dispenser. Now, the idea came from a couple of things that I've been working on. One of them that I started 4 years ago. When I first got into 3D printing, I decided to make a manual candy dispenser for my grandchildren. Actually, it was a project that we could all work on. It didn't work that great, but you get the idea. It was twist a little knob, dispense the candy, and it gave them something to do, and it was a project we could all participate in. Well, fast forward 4 years, I recently completed an online engineering program, and one of the first things that they had us do was come up with a mechanical engineering design based on food. And I thought, maybe I can improve upon what we built 4 years ago. So that was the idea. In this video, I'm going to talk about the design process a little bit from a mechanical aspect. We're going to talk a little bit about electrical engineering. These things are going to be very simple, so for you makers out there that are experienced, this is basically for the students or the kids that happen to be watching this and want to learn some of the basics. So I guess with that, let's get on to the whiteboard. All right, so let's talk about the mechanical part of what I had to go through to design this thing, in addition to some of the things that I learned. First of all, my idea for this was to have a jar to hold the candy on top, much like the original. There would be 2 discs, one immediately under the candy, and then one driven by a gear below it, and then a little chamber in between the 2 discs that would hold a certain portion of candy. Now, my idea was portion control with a time delay. Now, the time delay ends up being the time that it takes for the little opening that lets the candy out to go all the way around, fill itself back with candy, and then dump it again. So, what I ended up doing was, first of all, finding a gear motor to drive this whole thing. I had no idea what kind of speeds of gear motors I would find, so as I'm looking on a website that sells these things, I found one that was as slow as 28 RPM. So my gear motor could be 28 revolutions per minute. Now, 28 revolutions per minute, if we round up to 30, that gives us 1 revolution every 2 seconds. That's a little fast for what I need it to do. I need it to actually be about 10 times slower than that. So that's when I came up with the idea for the gear driven. That way I could slow the speed down that the disc turns to let the candy out, but keep the same RPM or speed of the motor. Well, in order to have a speed reduction, the drive gear needs to be very small, and the driven gear needs to be larger. In this case, I found a drive gear that had 20 teeth, and it was quite small. And I knew that I would have to have something with 200 teeth, something 10 times larger, in order to slow that down. So my driven gear would have 200 teeth. That being said, I had no idea how to size this gear because I was going to 3D print it. I had no idea what the diameter of this gear was going to be and how I would get the pitch of the teeth right. As I was looking for gear motors and drive gears to attach to it, I came across a formula and some values that I was not familiar with. The formula is this: module equals the diameter of the gear divided by the number of teeth. Now, module is actually a number that tells you the ratio between those two. And as long as every gear has the same module, in this case, they will mesh together, much like this. They will mesh together and should be able to drive appropriately. So what I ended up doing was taking the 0.5 that was specified in the gear that I was going to buy, and I needed to find out this number, what the diameter was going to be, because I didn't want it to be overly big. And I knew the number of teeth had to be 10 times of the one that I was buying so I could slow the speed down by a factor of 10. So what I ended up with is 200. And if we take 200 times 0.5, this number is equal to 100. And in my case, it's millimeters, which is just shy of 4 inches. This is actually one of the first gears that I printed, and I ended up changing this hole. But this hole is where the candy gets dropped out of or dispensed from as it comes around to empty the little chamber that got filled with the other disc. Now, the disc and the gear are on a common shaft, so they turn at the same time. All I had to do was offset the holes, so the first one would fill the chamber up, and then after it got past the place where any more candy could get in the chamber, then this one comes around and lets it out. So this was essentially what I needed. I just had to figure out how I was going to 3D print a gear, and I'll get into that a little bit later. So my drive motor is sitting here with 20 teeth driving a 200 teeth gear. So this is slowed down by a factor of 10, which means it's turning at about 3 revolutions per minute. So if I take 28 divided by 10, this gear is turning at 2.8 revolutions per minute. And that gets me just about the speed and delay that I wanted for each dispense of the candy, if you will. So that's the mechanical portion that I learned along the way. And now we'll break into the electrical. All right, let's talk a little bit about that electrical. So here is a basic schematic or electrical drawing of just a battery and the motor. So if we take a battery and we run a wire from one side of the battery to one side of the motor, and then from one side of the motor back to the other terminal of the battery, we should make our motor run. Our motor will run all the time because there's no switch in here to open up the current flow. So this isn't what I want to do, but I wanted to show you just the basics of hooking a battery to a motor. And we call this a complete circuit because the wires go from the battery to what you're powering, from the other side of what you're powering back to the battery. Complete circuit. Now, what I want to do is put a push button on the front of the candy dispenser. So this is the schematic symbol for a push button. So what you have now is, if you look at it just the way it's wired, then the motor will not be running. We have an open circuit here. This is the same thing as cutting the wires in half or removing one of the wires from one of the terminals. So this is a very basic schematic, but I want everyone to understand that hasn't ever done anything like this, just exactly what's going on. So this is my push button. So every time that I push this push button, it ends up looking like this in the circuit, and it shorts those two contacts together, and we end up with our complete circuit to drive the motor. All right, I want to go one step further. I want to put a push button in here to start the whole process, but once I push the button, I want the motor to continue driving until the candy dumps out, and then stop. And then when you push the button the next time, it'll do one more revolution the same way. And the way that I hope to do that is to put another switch that we call a limit switch or a micro switch in there. And something on the candy dispenser will trigger that switch. But I want this to be a unique switch. It's not going to be drawn like this for the one that I want to use. It would be drawn like this. And that is called a normally closed switch. And that means with nothing touching it, no one interacting with it, that in that normal state, it's a closed circuit. So that means it's a switch that is on. What I want it to do is be on all the time until it comes around to a certain spot on one of the gears or on the axle or something that will bump this and open it up so that we no longer have current flow. And then to start the whole process again, we push this button, and when we push this button, we complete the circuit momentarily, but it's enough time for this to fall off of whatever opened it up in the first place, the little physical. I think I'll probably end up printing a stud on the gear, on the driven gear. But whatever I use will have to push that open once it comes back home to its final position. So that's a very, very simple circuit, but I wanted to kind of go through it for anyone that's never done anything like this so they can kind of understand electricity, current flow, and the types of switches that I'll be using in this project. So with that, let's talk a little bit now about the program that I used to do the three-dimensional drawings that I'll ultimately put into the 3D printer to print the pieces. So let's get on with that. So this is the 3D drawing program that I've most recently been using. It's Fusion 360, and it's made by a company called Autodesk. Autodesk also makes lots of other industry standard drawing packages like AutoCAD, and there's several others. Now, the price tag on this is pretty steep, but fortunately they allow people to use it for a non-commercial use. There are some limitations, but so far they haven't stopped me from doing anything that I want to do. With that, let's talk a little bit about how I was able to get this gear drawn up, and also I was able to bring in the micro switch or limit switch that I was going to use in the project in its actual dimensions. I imported this from a manufacturer, and then this is the bracket that I drew to support the switch. Now, one of the cool things about this is you can actually see if it's going to be in the position that you want it. And if you see here, this is actually how it came out. This little stud that I drew just is barely tall enough to hit this switch as it comes around when it rotates. And true to form, this is exactly how it was in real life. When I got this all mounted in this position, that's exactly where it hits on the switch. It just barely hits it, but it's enough to make it function. Now, let's see how I got this far. So let me get to the new drawing here. There is a tool that can be imported into Fusion 360 that generates gears. And when you click on the gear generator, you can come over and supply it some parameters. Now, earlier I said the drive gear that I was using had a 0.5 millimeter module. Now, the number of teeth that I want in this gear, I want 200 teeth. The gear height, that's basically the thickness. I believe I went with 4 millimeters. And the pressure angle was another one of those things that was defined in the specifications of the drive gear that I purchased. and they were using 20 degrees, which I've been reading and finding out that that's kind of a standard. So we'll go with 20 degrees, and when you click OK, then it runs through some scripts in the background and it generates the gear. And that just couldn't be easier. It took a little while to get the this little add-on installed and get it up and running in the program. But once I did this, then I was able to modify my gear, add the hole, and add the axle hole and the little places for the set screws, and it just all came together very well. So I'm really happy with this program, and I plan to continue to use it until I find something that works better. With that, let's get on with the assembly. Okay, let me show you some of the pieces that I have. All the 3D printing is done. A few of the pieces had to be done a few times in order to get them right, but here's what I have so far. So this is the base of the candy machine. You can see I've already got the push button installed, and this is the micro switch that I had talked about earlier. Now, the micro switch gets actuated by the spur gear, this little stud. This will sit in here like that, and as that rotates, it will come around and press the micro switch and hopefully stop it at the appropriate time. This is the gear motor that I talked about. It's a 12-volt gear motor. As you can see by the markings here, 28 RPM. The small gear is the 20-tooth gear that I purchased, and this is the 200-tooth gear that I printed. And the opening is for the candy to come out. So that is that. I also bought a few of these small bearings so that I could keep the axle nice and straight and give it something smooth to turn on. I've already started the assembly a little bit, but I wanted to show you the pieces and complete the assembly along the way here. This is the top of the candy dispenser. The jar full of candy will screw onto this, and that will be that. Small opening for the candy to come out. On the inside of this is another small disc that will come around to allow the candy to come out. Fill in, or fill up, I should say, this little chamber. There's your portion size. And then I also needed a way to space the top from the bottom for the height of the candy chamber. So I was going to purchase some standoffs, and I decided to print my own. Now, I probably should have waited to put these little inserts in so that you could see how that's done. But essentially what these are little brass inserts. I believe they're called nutserts. And these are really cool. There are a lot of YouTubers and people doing 3D printing that use these all the time as a nut to be able to assemble your 3D printed pieces. And how it works is I have one here that was a design I ended up not using. You print a hole that's just slightly smaller than what this is, and it will press in there just a little ways, and then you take a hot soldering iron and push it in there, and it slowly melts the plastic. And if you're very careful, and it doesn't take too long to get the hang of it, you can get those to go in there just nice and flush and not do any damage. Now, I learned a valuable lesson. I used them on the micro switch bracket, and I had the little insert so close to the outside edge that it sort of warped that plastic, but that won't be seen, and it doesn't seem to hurt the structural integrity, so I think we're going to go with that. But lesson learned, next time I'll leave a little bit more room for some extra plastic around the nutsert. Anyway, what else do we have here? We have, yes, I showed you the gear, the chamber. I'd say let's get started with assembly. Let's start on this soldering action here. Now, one of the things that I've learned over the years is that even though the solder has a rosin core in it to help the solder flow, a rosin pen certainly helps. If you add just a little bit of flux to the things that you're trying to solder, it helps the solder flow much quicker and much easier. So it can be a little messy at times, but it certainly seems to help. Now, I don't know if you can see this or not, but there are labels on here. This is the common terminal that I talked about earlier. This is the normally open connection, and this is the normally closed. So I'll be soldering wires to this one and this one. now I have a bench power supply up here that I can adjust to 12 volts. And keeping the polarity correct here, we'll see how this works. And with any luck, as it comes around and hits the limit switch, it should shut itself back off. Looks like that worked. Looks like the dump opening in the gear is past where it needs to be to dump the candy. And if I press the button, it should make yet another revolution. And you see, maybe you can't see, but the little stud comes around and catches the limit switch, shuts it off as designed. I think it's time to load this baby up with some candy and give it a try. All right, during that little break, it gave me some time to go find the M&Ms, load up the jar, get everything situated so that we can try this baby out. So let's press the button, start the motor, chamber gets loaded full of candy. As the bottom disc comes around, it dumps it into the tray. Hopefully it stops. There's your time delay. And the motor stops. I'd say it was a successful engineering project. So now we can have a snack. Thanks for watching, everybody. If you like what you see, please take the time to subscribe and don't forget to click that thumbs up icon. We'll catch you next time. Thank you.